As you can see, my name is Arya Hakimian. I am from C-Therm Technologies, filling in for the speaker that wasn't able to make it here today. The goal of the session I would like to present to you today is just evaluating some of the importance of thermal conductivity data with respect to geothermal mapping and analysis. So today we're going over some different techniques, methods as they relate to the different sample types, and provide you with some application data on this topic. So for an agenda, I'll do a brief introduction. Again, really taking a dive at the different thermal conductivity aspects as it relates to geothermal. Going over some of the different methods that are available for characterization, with some application data and conclusions. So with that, we'll jump into it. First, looking at really, a brief introduction as to how this all relates to geothermal. Of course, for many here, this is not a new topic, but really focusing on the aspect of renewable energy is something of great interest for many researchers and many groups. Taking a look at how the heat available at these different subsurfaces can be used to help introduce different technologies for these renewable aspects. Of course, there are different regions, different sample formats, different conditions that will be investigated, but really tying into the fact that the heat sources under these underlying surfaces, the materials that surround those, the bedrocks, the basins, they can all have a very large influence on the overall performance and as to how this all correlates to the end product. Now, you see heat mentioned, of course, throughout this introductory slide, and many of the times this, of course, ties into thermal conductivity. Myself, for the past few years at C-Therm, really focusing in on thermal conductivity as a key performance metric for many of these applications. At a very high level, thermal conductivity relates to the ability of a material to transfer heat. Now, of course, in its most simplistic form, thermal conductivity denoted in units of watts per meter Kelvin. We always like to introduce or explain the fact that, of course, this is a property that will be heavily influenced by the conditions of the different environments and the testing. So the temperature, pressure, saturation, these are all factors that can tie into the measurement of conductivity. Now, as mentioned, again, for a performance metric, the aspect of thermal conductivity can be very important for your overall design of these different extraction techniques, material selection used for these products, simulation. These are different aspects of we've helped and collaborated with different groups over the years in an attempt to really benefit and improve on the type of data that is being collected. Here, this is an example of some geothermal mapping. We worked in collaboration with our local university, the University of New Brunswick, located in Eastern Canada. There we've partnered as well with the local government in doing these types of analyses. This is a geothermal map of the province. Some of the work that was also tied into this study investigated the different thermal properties of the surrounding geological materials, as well as different sample types under these varying conditions. Now, for a bit of a method overview, again, not to be fully inclusive or covering all possible different aspects. But of course, there are different methods available depending on the types of samples that you're working with. At a very high level, steady state and transient based methods are the two larger classes for these types of analyses. For the purposes of the presentation here today, really taking a look at the different transient based options that are present for these types of measurements. We like to mention transient as they are generally quite flexible with the types of samples that are available to test, providing fast measurements, relatively flexible sample sizes, and be able to test under different conditions, of course. Now for some different application data that we collected, again, this was quite some very basic examples for the presentation here today, but really allows for the explanation of how this can be used for perhaps some more in-depth studies. First, taking a look at the transient line source. This is the method that we use to collect the data that we'll be presenting here today. It's a needle probe style sensor. Many of you, I believe, may have experience with this type of technique, specifically as it conforms to the ASTM D5334 standard testing of geological samples, soft rocks, things like this. With the TLS, generally we've seen the use involving different polymers, fluids, as well as surrounding geological matrices. As far as the overall method, how the testing is done, these transient solutions have a general overarching idea that a heat pulse is delivered to the sensor, and based on the rate of change that is observed over the course of the measurement, the thermal properties are thus determined. This is, again, related to the change that's observed over the finite time of the measurement. Some of the experimental data that we'll kind of present here today is on some aggregate materials. Of course, aggregates can vary in sizes depending on the surrounding environments and the depths that you are studying. In this study, we worked on quite fine to medium-sized aggregates. We took a sampling of this sand type sample and use the TLS needle probe to do the analysis. Now, you can see the image on the right. The needle probe is fully inserted down into the sample matrix. And with this material, it's quite ambient temperature, ambient pressure. There wasn't considerable environmental control adjusting these types of parameters. But one thing to take note is the testing as the measurements are taken, introducing a fixed delay to ensure that each measurement, you're not significantly introducing additional heat being introduced into the sample, other than that is of what is needed for the actual measurement. I'll talk about some testing that was done under varying temperature conditions, seeing how the effect of thermal conductivity can vary as a function of that property, as well as looking at the influence of saturation, as we know can have a bearing as well. So the image on the right here, there we go. So taking a look at the dry versus semi-saturated state of the material. These measurements here simply showing that, of course, under a saturated condition, you're experiencing a much higher thermal conductivity compared to the dry matrix. If we think about the sand sample, one of the things to be noted, of course, is that the spacing in between the individual particles can be saturated and devoid of that airspace. So by the water coming in and filling in those different spacings, we are seeing a higher effective measurement of that thermal property. The other aspect that was looked at, again, here was the measurement across a temperature range, simply noting the fact that as you're increasing the temperature of your samples throughout your measurements, we can see that the trend is showing a net increase as a function of that increase. So these are just some very basic examples, again, taking a note that these are types of materials where the thermal conductivity values can be used for these different types of investigations. Of course, if you're looking at the borehole or the design of the surrounding matrix, how this can correlate to that type of measurement. There are, of course, other methods available, and for the purpose of the time here today, just to give a few different options. Testing of oils, fluids, as was mentioned earlier, the surrounding matrices may perhaps introduce certain materials that are of interest for extraction, oil being one that can potentially have some economic and financial considerations as well. But really taking a look at how the pressure of the overall environment, as well as the aspect of temperature, can come into play. Just some examples of how the taking a measurement of a specific sample at a kind of a constant temperature, but under these different pressures, can of course have large changes in the overall thermal conductivity of the expected medium. The image on the right, this is just some of the data that was collected in conjunction with that previous study I mentioned with the University of New Brunswick, C-Therm, and the locally governing bodies of New Brunswick, taking a look at how these different materials can be measured, and of course, depending on the data that you're comparing to, understanding the method that was used, it's always good to get a baseline and understanding really the overall performance of these samples, and ensuring that if you are comparing to previous data, making sure that there is correlation there or understanding where these differences can come from. So in conclusion for the, this talk here, I really just wanted to highlight the fact that using these transient-based methods for thermal characterization provides you with a aspect of accuracy for representative thermal conductivity data collection. Shown here, the saturation and increasing temperature of that sand using the TLS method were noted to have an increase on the thermal conductivity of the materials shown. But really, again, the overarching idea is that the highlighting of using representative test conditions for your studies can really be a valuable tool to ensuring you're getting the most specific and representative application data for your specific investigations. So with that, I'd just like to close out saying thank you. Again, my name is Arya Hakimian, application scientist from C-Therm Technologies. So thank you for your attention, as well as thank you for the organizers for inviting to the conference and taking care of all the amenities and organization here today. So thank you.